Thanks for the introduction. Our work is about accelerating this tree traversal. So although it's called BVH, that is a data structure used for ray tracing, but actually the technique can be extended to other type of general purpose trees, as already being demonstrated by the first talk, where they use, basically the page table can be organized as a tree, such that, ray tracing course can be used to accelerate such kind of tree traversal. So this work, by the way, the leading author is, Yavuz, Tozlu. He's my PhD student, but unfortunately he cannot get here. So there I am. So before we jump to any details, so let me first share with you the key ideas or the main takeaway message. So the main takeaway message actually is that for ray tracing, or more in general, all these tree traversals, they are actually highly divergent. So as a result, as we will see later on, there will be RT cores will have low hardware utilization rate, and the reason is mainly because of what we call as completely idle or these early finishing threads. So we will see that in a few minutes. And to deal with that, compared to previous works in terms of dealing with divergence, we actually are not trying to avoid this divergence. Instead, what we found is that we can actually leverage this divergence. So the idea or the key observation is that if you look at tree traversal, and in terms of ray tracing, the tree traversal is done in the depth-first search manner. And all these, actually, even if you go with breadth-first search, so all these tree traversal operations, they're actually inherently parallelizable. So as a result, our idea is actually the following. So how about we use those idle threads to help with these busy threads, such that the overall latency can be reduced and the overall hardware utilization rate can be improved. So what we show in our paper is that this idea actually leads to low hardware overhead and a significant speed up. So now let's get into a little bit more in ray tracing, because that's the workload we evaluated in our work. So ray tracing, so as we already probably heard from the first talk, so ray tracing is a technique to generate these high fidelity visuals. And the way it works is that, imagine that we have a camera, and then we have the view plane. So the idea is basically to figure out what is the color of each pixel in the view plane. So what we do is that we shoot one or more rays from the camera through that pixel, and then let the ray bounce through the 3D objects. So during the process of bouncing through the 3D objects, some rays basically reach the light source, some rays basically fall into the background, basically disappear, does not touch any object. So that's why you can see, there are certain levels of divergence. And later on, I will show you the code that you can see, obviously, the divergence will happen in that manner. And to accelerate this, the ray tracing process, basically, we want to test whether a ray hits some object or not. So the typical approach is to use something called acceleration structures. And one type of acceleration structures is called this bounded volume hierarchy. So basically, it is a tree structure, basically capture all these 3D objects in the scene. And then finding a hit, or basically following a ray to see whether, what kind of object it hits, it basically becomes a tree traversal problem. So what we have over there is that when we use RT cores or when we use GPUs, because we have so many rays to trace at the same time, so as a result, we have a massive parallelism. But we have all these concurrent tree traversals, but they do diverge extensively. So first, let me give you some data to show what is the performance bottleneck. So in this figure, basically, we can see that this figure is about path tracing. Path tracing is one application of ray tracing. And this one, the idea is basically, when a ray reaches one object, it will generate a second rays, basically keep bouncing around in different objects, and until it reaches a preset number of times of these bounces. And the more bounces, typically you get higher fidelity visuals. And from this figure, we can see that the distribution of the pipeline stalls, the majority of the stalls are actually caused by these ray tracing operations. And over there, I'll get into that a little bit more detail. So let's take a look at actually the source code of these ray tracing operations. So over there, if you look at the code, so over there, as you can see, this for loop is what I just mentioned. So this one basically says, when a ray reaches an object, it will keep bouncing. So this, this variable basically sets the upper bound of how many bounces this ray needed to keep going forward. And inside the loop body, this one basically, this trace ray, this would be the tree traversal operation, would be offloaded to the ray tracing cores. All other operations in this kernel actually would be run on the CUDA cores. So again, just look at this one is actually, you can view this one as a kernel function. And inside of the kernel function, there is this special complex operation, which is called trace ray. And this operation will be offloaded to the ray tracing cores. And this one, basically what it does is it's to perform that tree traversal of that bounded volume hierarchy. So from this one, as you can see, one source of the divergence coming from actually this tree traversal process, because different rays, as I mentioned, they may reach their target in different timing, and some rays may completely miss all the object, so they would terminate very early. So that's one source of the divergence. So that's what we see here is, when we have this trace ray operation, so different threads within a warp will experience quite a different latency of that instruction, or of that operation, if you want to call that. And then another major source of this divergence actually coming from this if statement. This if statement really says, if the ray completely misses the scene, it does not need to participate the subsequent bounces. So that makes sense, right? So as a result, it will just say, okay, let's break out of this loop. But unfortunately, as we know, when the warp is executed, all 32 threads participate in this SIMD execution manner. So as long as there is one thread saying, okay, I do not want to, break out, then, you will have, completely idle threads coming into this operation. So that's basically the second source of this, hardware underutilization. And if you look at what we collected from this profile, from different things, as you can see the distribution, a significant portion of the threads basically are due to these completely inactive threads, and a certain portion also due to these early terminating or early finishing threads. So another way to look at this one is actually look at this picture. So this picture on the top, basically what we describe is kind of like the thread status of one warp, during the execution of that, trace ray instruction. So as you can see, for that particular warp, at the time when it is executed, many threads within this 30 threads warp are actually completely idle. And also, among those busy threads, some finish early and some finish late, right? So that's basically give you an idea of how this divergent behavior showing up during the thread execution at runtime. So our CoopRT idea is to say, okay, how about we leverage those idle threads such that they can steal some work from those busy threads. So as a result, what we achieve is basically the bottom part. So basically, as you can see, those blue color ones are actually the helper thread. So they are busy now to perform some useful operations for those busy threads. So as a result, the overall execution time will be reduced and the overall hardware utilization will be improved. So now let's see, how we do that. So as I mentioned, basically we leverage those idle threads. And then the observation is that these, for example, this depth-first search in terms of tree traversal is inherently parallel. So as a result, we can use those idle threads to perform some useful operation for those, busy threads. So let me illustrate that one with this kind of a simple example. So assuming, okay, so this is a tree. So let's assume that we perform this depth-first search. So just a quick recap in terms of this depth-first search. So what we do over there is that, based on, when we check a node, we check whether its children need to be checked for intersection, in terms of hitting that object or not. And then if they do have a hit possibility, then we push them into a queue. So assuming that the order of this traversal is that we first check this node, and then we basically check this node, and then because its children may have a hit, so we push this one into the queue, and then push this one into the queue as well. So after we do that, now we say, okay, let's pop from this queue and then continue the search. So that's the case with baseline. So basically, you can view this one as we get this node and check its children. We push in this node into the queue and process this node. Okay. So currently, what we have in the baseline is that this one is sitting in the stack doing nothing. So in the case with CoopRT, what we do is that rather than letting this one thread to deal with this complete traversal process, we will let the helper thread to basically basically take out a node from this busy threads stack, and then start from that point, and then following exactly the same depth-first search logic. So that's basically the idea. So the only thing that you need to be careful is that because we want to find the common, the closest hit, so that's the requirement for path tracing. So as a result, all these helper threads, they needed to update the same, in terms of their min threads, this closest hit value. So that variable is called this min t hit value. So in order, as long as we can do that, this parallelization would be valid. So the correctness would not be affected. And that's basically what I just described in terms of the algorithm. So the details we probably can quickly skip. And in terms of hardware implementation, so the key thing that you want to notice is that inside of the RT unit, each thread will have one tree traversal stack, maintaining all those nodes that during the traversal process, which are, the nodes are pushed into the stack. So all we needed to enable CoopRT is that we can, as long as we can enable other threads to access, different threads traversal stack, then we can enable this work, basically the work item or workload stealing. So that's basically the main thing. And of course, as long as we needed to ensure the condition that, the common closest hit value need to be updated correctly, we also needed to maintain, basically we add another field to maintain the main thread ID. So that's basically the key the key takeaway from all these implementations. The details are available in our paper. All right. And in terms of evaluating our approach, so we use LumiBench along with Vulkan Sim. And these are the kind of simulation setup, and as well as those 3D scenes. And if you look at quickly the results, so here we are. In terms of path tracing, we get a little bit over 2x speed up. And in terms of power consumption, because now we have higher hardware utilization, so we got higher power consumption. But when we combine this execution time and the power altogether, we roughly consume the same energy compared to the baseline. And also the same approach not only works for path tracing, it also works for other shaders like this, ambient occlusion as well as shadow shaders. So although the speed up would be a little bit lesser, the reason is those ambient occlusion as well as shadow shaders, they do not need to keep bouncing through the objects. So the level of divergence is not as significant as path tracing. So that's basically the reason of less speed up that we observed. And also another quick data point is the memory bandwidth usage. So as you can see, in terms of baseline, due to the hardware underutilization, the bandwidth is actually underutilized. And with CoopRT enabled, so we improve, we use L1, L2 bandwidth as well as L2 to DRAM bandwidth more effectively. So that basically, those increased bandwidth usage correlate pretty well with the performance gains that we observed. So in summary, the key takeaway idea is that the observation is path tracing or in general tree traversals or concurrent tree traversals, they are highly divergent. And our CoopRT idea, instead of making those workloads less divergent, we try to take advantage of this divergence. And the idea is to use idle thread to help the busy threads. And little bit hardware overhead, but significant speed up at the end. And our CoopRT work is open source. And feel free to check it out. And thank you for your attention. And I'm happy to take questions. Thank you.
Okay, thanks to the speaker.